So you're now going to be on YouTube. What'd you say, James? Oh, okay. Yeah, yeah. I can send out the links after this. I know I keep saying that I keep getting buried by 211 stuff. I'm trying to do this class as a guest and also, the big class. Um, all right. Thanks, Caitlin. So, what are the things we know? We know that um, um, in regions where V is constant, we know that the wave function is equal to some normalization constant, which I'm just using as A. Um, yeah, sorry, I'm reading chat. Yeah, I apologize for not getting that clear. I don't really have like a mailing list for 361 like I do for 211 times e to the ikx, where k is square root of 2m times the kinetic energy, which is E minus V, divided by h bar squared. And I apologize for every time I have forgotten that h bar squared. Um, there isn't any ad revenue, I don't think. At least I'm not getting any. I don't know anything about that, about how to like get money off of YouTube. But yes, if there were ad revenue, I would actually, if there were ad revenue, I would donate it to the Chicken Soup for Jack fund, the Get Well Jack fund. Um, so we know that this is what happens in regions where V is constant. And I should write plus or minus here to note that if, because remember square roots can be either plus or minus. Let's make this a little clearer. K equals plus or minus. So K positive means a wave going to the right, and K negative means a wave going to the left. Um, Now, we talked before about how when the energy is less than the potential, instead of wiggling things, you get exponential decays. And this formula right here will give you the whole thing because, you know, you get a negative under the square root sign, and that's fine. But one notation that we like to use, just to make things simple and to understand readily if something is growing or decaying, is to just reword this. If V is greater than the energy, then we can write this as AE to the kappa x. So take just the real part, where kappa is plus or minus the square root of 2m V minus E over h bar squared. So in regions where the potential is constant, we've got a piecewise constant potential, so this applies. The only solutions we can get are oscillatory things. So a e to the ikx means sines and cosines, and exponential growth and decay. We also have the continuity relations, right? So we know that at a boundary, we know that psi and psi prime are continuous. So what I'd like to do now is I'd like to take these ideas and analyze this system. So the first case we're going to look at is what happens when the energy is bigger than the potential step. So here, We've got two regions. We're going to have region A. Well, we'll call them regions um, 1 and regions 2. So are we going to have the case with K, with oscillatory things, or the case with kappa, with decaying things in these regions?
I'm just making sure this is the energy of the system is greater than the potential.
Yes, yes.
Okay.
So remember this funny case where V is greater than E, this happens when the kinetic energy is negative. Is that going to be the case on either side here?
No.
No. Yes, because the energy is greater than the potential on both sides. So that means that in region 1, um, probably shouldn't use Roman letters for that, right? So that
So
means,
even though, sorry,
go ahead, Isa.
so even though kinetic energy is negative in V greater than E, it's the previous one that has the imaginary component to it.
Yes, yes, because this I here, right? So think of a complex exponential produces oscillations, and oscillations are what you get for just a particle traveling through the air. So the I that's present here comes from the solutions of the Schrodinger equation.
Okay.
So this is from the Schrodinger equation. And the fact that there's no I here is because we have an imaginary K, and the I from the imaginary K cancels the I from the Schrodinger equation.
From the okay.
Does that make sense?
Yeah. Thank you.
Yeah, it's confusing. And then when I was taking this class, my professor would sort of like casually gloss over the fact that 1 over I was minus I, which is true, but I had to think about it. Um, so yeah, like the algebra for this can get a little muddling. So please ask questions. So in the first region, I have two possible wave functions, and they're both of this first type, right? I have, I'm just going to use black here. I have psi of x equals, and so I can have ones with positive k and ones with negative k, right? So ae to the ikx um, plus be to the minus ikx, because I can be either going left or right. And similarly in region 2, I can have the same thing where k prime is the one with the potential, right? I've just got two different k's. V minus e over h bar squared. So now I've got four unknowns, a, b, c, and d. And I need to think about what they all represent. So one of the things that helps keep this straight is like, what do your variables actually mean? So a here, let's make a list. Um, a, so we're going to imagine that we're throwing particles from the left at this thing. right? So we have like this potential barrier set up, and we are um, tossing particles in this way. Because I made a mistake, Ava, this should be E minus V. You're right. So A is the amplitude of the incoming particles, or the wave. So with that, what is B? What does that represent physically? Yep, and the amplitude of a reflected wave. So we're throwing electrons at some kind of potential barrier, created electrostatically, and yeah, some of those electrons are going to bounce off. So this is the amplitude of the reflected wave. Okay, continuing that logic, what is C? The transmitted wave. And what is D? Zero, yes. Why zero, Matthew? You're right, but tell me why it's zero. Yeah, the transmitted wave is not reflecting off of anything, right? Um, that would imply that somebody is over on the right-hand side throwing particles back to the left. So yeah, the transmitted wave can only travel to the right. So this is equals zero, and we can just cross that term out, right? So in this situation, it's always good to think about like what we know and what we're solving for. So Issa says, what is meant by the transmitted wave? So so remember we had an example earlier in class with we talked about the analogy between this and light. I haven't drawn it in the picture. Um, what what would happen? So let's make a metaphor with light, and this metaphor is quite exact. So let's say that this is glass and this is air. So if I shine light coming in to this piece of glass, some amount of that light will bounce back off, and some amount of that light will continue through. So A is the incident wave, and it's the same whether it's light shining on a piece of glass or electrons being thrown at an electrostatically repelling region. Um, B here is the reflected wave, and C is the transmitted wave. Now, I've drawn these as arrows rather than wiggling things here, but you can think of this as, all right, there's some sine wave with some large amplitude coming in. Some of that amplitude goes through, and some of that amplitude reflects back. Does that make sense, Isa? Good, good. Because keep that metaphor in mind. Because the idea here, like if we're trying to understand the reflection of light off of a pane of glass, um, and this is a very good metaphor as we discussed before with evanescent waves and total internal reflection, which we will return to. Um, A here is known because this is what I am doing to my system. B here is an unknown, and so is C. It's like we throw a bunch of particles at a barrier and we don't know how many of them bounce off or not. Charles says, if D existed, would it be light reflecting off of air? Yes, we could. So in this situation, I've drawn glass that doesn't extend forever. But, in my problem, I said, okay, let's pretend that this piece of glass right here, whoops, like just goes on forever and ever and ever. So our math is simpler. But next, once we're done analyzing this situation, we will analyze a situation where the piece of glass doesn't go on forever, right? Where this is some finite thing and where we could have, a situation with light, okay, this goes here and bounces off of that barrier, that interface. Some of it comes back and some of it is transmitted over here. So after we're done with this one, we will have one with a D and an E. But in our first situation, um, we're not going to consider the situation where we've got another interface off to the right to have even more reflections from. Does that make sense? Great. All right. So again, we're not going to have these around for now. So what I know, what I really want to solve for is B and C as functions of A. Um, Isa, is this kind of what you had in mind of like how do we use the math we've learned to actually solve for stuff? Okay, good. Yeah, I know class last time, I wanted to do this last time, but then we had that really abstract but really useful conversation about eigen stuff. Um, so we want to find B and C. My tools are being funny. As functions of A. What tools do we have? So scrolling back up to the pile of things that we know, of the things I've listed, what tools do we have to relate A, B, and C together? Yeah, okay, so Matthew says that the wave functions must match, so the continuity at the boundary. So what we know is that psi 1 at the boundary must equal psi 2 at the boundary. And the other thing is the continuity one. Oh, the continuity of the first derivative equals psi prime 2 of 0. So in order to find B and C, I'm going to take these two equations and write down um, what they tell us and set these things equal and solve. So we'll actually do the algebra for this one. So let me write down in words what we're doing. Actually, switch here. So we're using the continuity of psi and psi prime. Here, when I write psi prime, I mean the derivative of psi. Um, to find B over A and C over A, which are the reflection and transmission amplitudes. Okay, so the first condition, let's see, psi 1 is the A and B one, and psi 2 is the C one, right? So I have A e to the ikx plus B e to the minus ikx equals C e to the, whoops, I k prime x. And then I'm also supposed to do this, but where I take derivatives of both sides. Now, the derivative of e to the ikx is ik e to the ikx, right? Whenever I take a derivative of an exponential, I pull down all of the stuff other than the x in that exponent. So this gives me, for my second equation, a ik e to the ikx plus b, whoops, minus, right, because I pulled down the minus sign here, minus b ik e to the ikx minus ikx equals c I k prime e to the I k prime x. So this is a system of two equations and two unknowns, right? I don't know B and I don't know C. And solving these two equations is pretty simple because when are these two equations true, right? Are these equations true for all x or are they true for a particular x? X equals 0, exactly. So if they're true only for x equals 0, what is the algebra thing that occurs to us to do? Like, how does this simplify? Plug it in. Okay. What happens? Yeah, right. Plug it in. But what happens when I plug in x equals 0? Yes, Charles, all the exponentials are Zippo. And you thought that I was going to have to do hard garbage, right? Exactly as Yanshu says, my two conditions become so I have A plus B equals C. And let's see, I can divide through by I in my second equation. I have Ka minus Kb equals K prime C. So now I have to solve these two equations. Um, there are any number of ways to solve this system of equations. I kind of like substitution because it's guaranteed to always work. Um, I know there are other kind of fancier ways to do it. A equals C minus B. So KC minus KB minus another KB equals K prime C. Can I explain K prime? Yes. So remember, um, K is the square root of, so in general, let me, because I did gloss over a notation thing. So in general, K at any position x where x is constant, where the potential is constant, is the square root of 2m e minus the potential at that x over h bar squared. You remember that, Charles? Okay. So this means that we have two different k values, right? K is the wave number of the particle. The higher it is, the more momentum the particle has. K is just proportional to the momentum. It's either momentum times or divided by h bar. So what this means is that K for x less than 0 is, well, we'll write it this way, K1. So V is 0 there, right? So this is just square root 2me over h bar squared. But K in region 2 is the square root of 2m e minus v naught over h bar squared because the potential is different there. So I've got two different k values on the left side and on the right side of the step. And for simplicity, we'll call that one k and we'll call that one k prime. I know this notation is confusing as hell, right? And here's why. The problem is that the mathematicians use prime to mean derivative, and the physicists use prime to mean the other one. So here, this prime means the other k, and the prime up in psi prime meant the derivative of psi. So I am mixing the way physics people use prime and the way mathematicians use prime. I feel dirty using the mathematician one. Yes, Yenju, V here is similar to U and to potential. Um, yeah, I guess I should write U here. Technically, usually U is a potential energy, and V is a potential per unit charge. But in practice, physicists kind of like use them interchangeably. Um, Jack sent me some notes. Oh, the notes use U, so I will switch them over to U. Yeah, we kind of play fast and loose with notation. So yeah, I'll E minus U naught. Yeah, sorry about that. In like conversations between physics professors in a research lab, there is a whole lot of waving hands and saying, "You know what I mean." So U naught here is actually potential energy. You're right. If I meant potential energy per charge, I should say V. So, yeah, you know, I mean U here. Everywhere I've written V, I mean U. Let me just add a note. Um, Using U and V interchangeably. Sorry about that. So, did that answer your question, Charles, about the K prime? Good. So now let's continue doing our algebra. So I have this formula, bringing that down here. This tells me that, kind of unifying everything on the same side, this is the 2kb equals, let's see, that goes to the right, um, k minus k prime c. You know, actually, let me back up. I am going to back up completely because I realized I did something dumb. A is a thing we know. A is the one that we know, so I ought to be doing algebra up here and solving for B in terms of A. Like, why do I still have two unknowns? So I did a stupid. It's the right technique, but I'm solving for the wrong variable. Um, Let me now plug in what I got for B. So now I have Ka minus Kc plus Ka equals K prime C. So carrying that down, sorry about that, I get 2Ka equals K prime minus Kc. So C equals 2A, well, 2Ka over K prime minus K. And then we can plug this back in and find B. So B equals C minus A. So B equals 2Ka over K prime minus K. And then I'm going to write the A that I'm subtracting with a common denominator. So AK prime minus K, or minus AK. So there's a common denominator there, right? And then, let's see, I've got 2Ka minus a Ka. So this gives me Ka minus K prime A for, whoops, what have I messed up? Oh, that's a plus sign. That's what I messed up because I've got two minus signs here, right? Um, Careful, Yanju. It's not three. Um, oh, yeah, it is three. You're right. What did I goof up here? Yes. I'm going to need to check the algebra here because I'm pretty sure I have, in fact, made an error someplace. Yes, I have. I have made a sign error somewhere in my algebra that I will need to find. Um, Please.
Walter, it should be K prime plus K.
It
and the
should be,
denominator for c.
oh, the denominator should be k. Yep, that would do it. So let me figure out where that,
Yeah, and up here, above here, you can't see what I'm pointing to, but
yeah.
it
Um,
says B algebra B equals C minus A.
yeah,
And yeah,
yeah, so B equals C minus A, that's correct,
yeah. So
right? So then in the next thing, let me figure out where this is. So I have put in C minus A. So that next line is right. And then going down to the bottom. Yep, you're right. That's the minus sign that I dropped. Thank you. Um, so all of the k primes minus k's ought to be k prime plus k's. So that means that the numerator that I get ought to be, so that should be a plus sign, and that 3 should not be there. There we go. So what we've got, you know, tallying our results. Again, the algebra is not super important. I knew I had dropped a minus sign. Thank you so much, Jack, for helping me find it. Um, so C is 2k over k prime plus k times A, and B is k minus k prime over k plus k prime times A. These are transmission and reflection amplitudes. So that's one example of how to do this. Are there any questions about what we just did?
Those are the wave functions of the translational, or that's not the right word. Transmission,
Transmitted.
transflection.
Yes. So the wave functions that we wrote down, remember, were these things.
Mm-hmm.
So here are our wave functions. Now we know A, B, and C.
Okay.
So what?
And oh, those amplitudes.
Those are the amplitudes. Now there's one other form of this that you often see. So here we're talking about amplitudes of waves, right? But you might be interested in saying, well, if I'm throwing electrons at a step, how many of those electrons are going to go through and how many of them are going to bounce back, right? So these here, um, so Jack, do you do like number density? Have you done that with them?
no.
Okay. Um, so these are the amplitudes. But what about the fraction of particles? So amplitude, or rather amplitude squared, recall amplitude squared is proportional to the number of particles per meter. But we want the number of particles per time. So if I throw a whole bunch of particles, if I have an electron gun shooting particles at a boundary, what fraction of them um, will penetrate the boundary? So how do I convert from knowing a number of particles per meter to a number of particles per time? Ponder that for 30 seconds. I will be right back. I need to do something real quick and I'll be right back. All right, I'm back. How do I convert from knowing a quantity per meter to a quantity per second? Let's write it this way. Number per meter multiplied by something equals a number per second. What goes in that question mark? Velocity. Yeah, because that's got units of meters per second. And yeah, so this here is just velocity. So how do we get that in terms of our other stuff? Well, velocity is momentum divided by mass, right? And momentum is just h bar times k. So we know all of those things. So if we want the actual fraction of particles transmitted, um, so the fraction transmitted is going to be c divided by a times v, whoops, times, well, it's going to be cv over av, v prime here, because that's the velocity over on the right. Um, that's going to be c times h bar k prime over m over a h bar k prime over, or k over m, right? The only difference is that they have a different wave number on the left and the right. The h bars and the m's will cancel. Oh, shoot. I'm going to back up here. I made a mistake. I am so sorry. Um, yeah, let me back up and say something. Again, I am sorry. I'm a little bit scattered because I've been doing another class. So the amplitudes of the transmitted and reflected waves are A, B, and C. But the amplitude squared is the thing I actually want, right? So the flow of particles, people call it the particle flux, um, transmitted flux. This is going to be equal to c squared, because that's the particle density, times v prime. The reflected flux is going to be b squared times v. Remember, the velocity is different in different places, where v is h bar k over m. And then finally, the incident flux is just a squared v. So now if we want to ask questions like the probability, so we can now define something else. So as an example, the transmission probability, sorry, I tripped over that earlier, which people use big T for. So that's going to be c squared v prime over a squared v, which will be, so c, if we look up what that was, that's 2k over k prime plus k. So 4k squared over k prime plus k all squared. So that's the c squared part, times a squared. I'll label that. And then I'm supposed to multiply by v prime. So v prime here is h bar k prime over m. V prime. And now I need to divide by the denominator. So all divided by a squared divided by v, which is h bar k over m. This looks disgusting, but it's not so bad because a lot of these things cancel, right? Those things go away, and the a squared cancels this a squared. So t here, the transmission probability, is then 4k squared all divided by k prime plus k squared. But this k squared, I'm going to highlight, this k squared cancels with this k to leave me just one k in the numerator. And then I have this k prime giving me that for the transmission probability. So in the end, we got a pretty simple formula. The algebra in the end got a little bit icky, but does everybody understand what we did there in going from the amplitude c to the probability? Basically, we squared it, because remember the flux is the probability squared, times the velocity. So we said, all right, the probability that a particle goes through is the ratio of the transmitted flux, c squared v prime. Let me label that. So that's the transmitted flux to the incoming flux. So Isa, this is an example of like a fully solved thing. Any questions about that?
Hey, I'm sorry. I just have a quick question.
Sure.
So I know this was a while back, but this is all still like the first scenario that we were talking about if E is greater than V, right? We didn't jump
Yes.
away from that.
Yes,
Okay.
that's the next thing to do. Is to
All right.
go to E less than V.
Cool. Thank you.
Um, One thing just for completeness is that the reflection probability R is just 1 minus T, because if they don't go through, they bounce off, right? And if you do a little bit of clever rearranging of terms, you can get this to K minus K prime squared over K plus K prime squared. So now I'd like to do the case up here where E is less than V naught. So we can go through this more quickly because we kind of already know how this goes. So what's going to be the difference, looking back to our first page, what's going to be the difference in how we write down our wave functions?
No I.
No I in which piece?
Um, no. Well, no I in the e to the ikx.
Yeah, in A, B, or C?
Um, we have. Um,
Let me ask it this way. Which piece, so we're only changing, you think about making the potential bigger, so it's greater than the energy, right? Which region has the potential in it?
region 2.
Region 2. So this is only going to affect what happens in region 2, right?
Okay.
Does that make sense?
Yeah.
So, um, so here, region 1 stays the same form. Psi of 1 is AE to the IKX plus BE to the minus IKX. So we still have an incident and a transmitted wave. And these are traveling waves. But in region 2, now the kinetic energy is less than 0. And instead of E to the IKX, we now have E to the kappa x. right? So here, k is the wave number in the traveling wave region, but kappa is the imaginary wave number inside the exponentially decaying region. And again, the only reason that we use kappa here is just to make it clear which things are growing and decaying. So now psi 2 is c e to the kappa x plus d e to the minus kappa x, right? And these are functional forms that you know. You've seen these functions many times. This is an exponentially growing thing. Bloop. And this is an exponentially decaying thing. They make those noises. So which one of those is physically sensible for x greater than 0? You know, before we argued that we only had a transmitted wave going to the right, we didn't have a transmitted wave going to the left. Now we can do the same kind of thing and cross off one of these two terms. Which one do we get to cross off?
Would it be reflected because it's decaying, so it might not have the ability to reflect anything back?
Oh, do you mean you want to cross off like one of the ones in region 1? You want to just like scratch out that one?
Maybe.
So you could, but you could also think classically, like if I'm throwing tennis balls at a wall that, repels them, I expect them to bounce off. Like you kind of classically, if I'm throwing electrons at a region that is at higher potential than those electrons have energy, they cannot penetrate into those regions and they'll all come back at me, right? So we expect something reflected. Of these, C and D, which one can I cross off?
C.
Why?
Because you said that the tennis ball would bounce back, it wouldn't go through the wall. Speaking metaphorically.
Yeah, yeah. And yes, you're saying that, all right, both of these involve the tennis ball going through the wall a little bit, right?
Yeah.
But C looks like the probability for the tennis ball to go through the wall blows up as x gets large. D, at least, the amount of tennis ball that goes through the wall decays exponentially, right?
Mm-hmm.
So this one we know we don't have because this blows up as x goes to infinity, right? So now D is the only thing I've got left. Does that make sense?
Yeah.
So my wave functions then, psi 1 of x is again ae to the ikx plus be to the minus ikx, and psi 2 was d e to the minus kappa x. So I can do the same game as before. I know that my wave function is continuous. I know that their derivatives are continuous. So setting psi continuous, this gives me, well, you know, A plus B equals D. We don't even need to think about that one. And psi prime continuous gives me let's see, so I have A I k e to the ikx plus B minus B I k e to the minus ikx equals minus kappa d e to the minus kappa x. Now again, because we are at x equals 0, all of those exponentials don't do anything, and this just gives us ika minus ikb equals minus kappa d. I don't have time to do all of the algebra here in 2 minutes. We can pick this back up later on Thursday. Let me tell you what happens here. So this is a little funny. Let me solve this for b. So I'm going to divide through by I kappa. So I get b equals let's see, if I divide through by I kappa, this is going to give me a plus I kappa over k d. And this is a little bit weird because this is telling me that I have a reflected wave like I did before, but now its wave number has picked up an imaginary part, which is a little bit peculiar. And we will talk about what that means next time. Will you ever? Yes, Charles, and you actually mentioned that situation. So remember when you said, um, so here I've got my light that I'm bouncing off of the glass, and you wanted me to think about what happens if the glass is only like a finite amount thick. So the light reflects off of the front, but then some of it also goes through and reflects off the back as well. Remember when you asked us to do that? So there you'd have 4 boundary conditions. Psi and psi prime on the front edge, and psi and psi prime on the back edge. And they have like, how do I say this? They have different x, so one of them is going to pick up those phase factors, and we will look at that next time. Any other questions from anybody or comments from Jack of stuff that I either messed up or forgot?
No, you did a good job, Walter. Thank you.
Oh, thank you. That means a lot coming from you. Jack is one of our best instructors in the physics department, so.
Oh, I don't know about that.
So Jack, they tell me that you always start all of your explanations with, so suppose you want to make a bomb.
Oh, I wasn't aware of that.
You weren't aware of that. So we talked about nuclear physics or nuclear bomb physics last week. So now all of the students know how to make a nuclear bomb.
Yeah.
On the homework, there is a question that asks you to sketch the function and asks if it is smooth. Could you briefly explain how to check if it's smooth? So smooth usually means that the function and its first derivative are continuous. So one way to check to see if a function is smooth visually is if you have a function like this, it's continuous, but its first derivative is not continuous, right? It has a cusp there. If you want to check and see if its functional form is smooth, then take its first derivative and see if that first derivative is continuous. Does that answer your question? Sure. May you have a look with the reflected probability. For this one or the previous one, Yanju? The previous one. Yes, this one. So I didn't do the algebra here. It turns out it's just sort of tricks that if you, because you know that the reflected probability has got to be 1 minus the transmitted probability, because every particle has either got to bounce off or go through. So then if you write, um, 1 minus 4k k prime over k prime plus k squared, and you get a common denominator and you like cancel terms and do shenanigans, the thing on the right is what you get. It's actually pretty easy to see how you get that, because when you square everything out, like like I'll actually write it out because it's only like people who need to go can go, of course, but this turns out to be, and here I'm going to factor out the denominator. So this gets me k prime squared plus 2k prime plus k squared all over the same thing. K prime plus k squared minus 4k k prime, right? And now I'm going to do this with my eraser. 2k k prime minus 4k k prime just gives me minus 2k k prime. And then you recognize, you recognize this numerator as just k minus k prime squared. Does that answer your question about where that came from? Ganju? Good. Yeah. Yeah, it's just a stupid algebra trick. Alrighty. Thank you all so much. I will get this recording up on YouTube. Jack, are you still there?
Yes.
What do you have anything I should pass on to them about their homework?
Yeah, I would say since you haven't gotten through all the lectures on chapter 6 yet, that it should be due probably next Monday.
Next Monday. Okay. So what are the things that I need to absolutely make sure I do on Thursday? Tunneling.
Yeah, tunneling, and if you could do the, through a barrier.
Yeah, tunneling through a barrier.
Yeah.
Yeah.
I think that's basically it.
Yep. Yeah, that's the plan for Thursday. Yeah, we got a little off topic. We did the nuclear physics stuff, but we also did we had a really good discussion about how the Schrodinger equation is an eigenvalue equation.
Yeah, no, that's good. It's good to have that. Um, no, I think we have to postpone
Until Monday.
homework. Yeah, till Monday.